wait virtually.
Yep.
No? I think, shall we?
Yeah, sure.
All right. Okay, so we're going to make a start. First of all, we wanted to welcome you because it's a new year, it's a new term, it's a new everything, it's a new format. Diego, before we were running the seminar last year, but we decided not to run it virtually. So pretty much the whole of the pandemic, we haven't had a seminar. So welcome back. It's our pleasure to welcome you back. It's a pleasure to have Diego. I don't know if you want to say anything, Carol.
No, just happy to see everyone. And well, we're trying something new. So of course, if there's any feedback at any point, please just contact us and we'll take it into account. We're also Zoom newy, so we'll see how it goes.
Oh, yes. Please be patient with us on Zoom.
Yeah.
And nothing. So we'll try to make it as close or similar to what we had. So we are aiming for a medium-sized seminar where we still know each other, but anyone is welcome to join. We have asked Diego and he's okay with taking questions. So if you have one, you don't have to wait until the end. You can probably unmute your microphone and ask away. So we're going to try to keep it as informal as usual. The only thing is try to keep your microphone closed, obviously, and your camera off if you're not asking any questions, because that will help with the bandwidth for everyone else. And I think that's it. So it's my pleasure to introduce our first speaker of the year, of the term, of everything. Diego Garlaschelli from the IMT School for Advanced Studies Lucca and the University of Leiden. And Diego is joining us in this new kind of format, which we are calling Fresh from the Archive. So Diego published a preprint about a month ago or a bit less. And we're going to keep trying to do this. So something that catches our attention on the archive, we're going to try to have a speaker. Obviously, it's kind of difficult. We have to have a speaker that responds on a short notice. Diego was kind of enough to do that. And we'll do this every other week, okay? So without further ado, the microphone is yours, Diego. Thank you for joining us.
Thank you. Thanks a lot. Yeah, thank you all the organizers, Renaud, Rodrigo, and Karel. And yes, so actually, this is really 10 days now on the archive. So it's really fresh. So actually, you were very, very quick in asking me to asking my availability for delivering this seminar. So which by the way, I'm really honored about. So I'm very honored to start this terms series of these seminars at the Mathematical Institute, the University of Oxford. I have to say I'm really happy also because, I mean, even if only spiritually and remotely, I'm back in Oxford for a little bit today. So Oxford is where I spent part of my time as a postdoc at the Captain Complexity Center at the Said Business School with the Felix Reed-Zokas. And so I've also, I mean, spent time attending to seminars at the Mathematical Institute, the Physics Institute. So I'm really happy being there back. Hopefully I will be there in person anytime soon back again. Okay, so the topic of this talk is network renormalization. This is joint work that I'm doing with two PhD students. So one is Elena Garuccio, who was a PhD student for a big part of her time at the Lawrence Institute of Theoretical Physics in Leiden. And the other PhD student is Margherita Lalli, who is currently doing her PhD at the IMT school in Lucca. So I'm really indebted also to them for the time and effort and expertise that they devoted to this project. And okay, so why is this network renormalization framework necessary for us? Well, actually, you see there are two magic words here, multiscale and without geometry. So multiscale, because as you will see, the aim of this renormalization approach is that of providing a framework to coarse-grained graphs at multiple scales simultaneously. And I will try to explain what we mean by this. And at the same time, we try to do this in a way that does not assume the presence of geometry. Well, in the strict sense of nodes having coordinates in some embedding space. So, but let's see why these elements are important for our discussion here. So clearly, if we think about ordinary renormalization, so real space renormalization, where the object of the coarse graining is a lattice, then clearly the defining units of the system at a given scale are identified through the coordinates of nodes. So basically, due to the fact that nodes have natural coordinates in some metric space, you know who the neighbors of each node are, and but the coordinates are necessary not only to identify, well, not really to identify neighbors, because of course you can identify your neighbors even in an arbitrary graph, but they are really necessary in order to define the scale factor. So in the end, the renormalization is all about a scale transformation and then imposing some invariance upon some scale transformation. So if you have a generic network like the one on the right of the screen, then there may be no embedding in a metric space possible for the nodes of your network. And this basically prevents you from defining what is the length scale that you should use in order to apply the scale transformation. So to identify which nodes end up being participants in the next level block node that you're going to define. So I will use block node as the key, well, as the generic word to indicate the coarse-grained nodes. It's like from a spin to block spins in statistical mechanics models, like in the Ising model. And here we imagine moving from a node or a microscopic node to a block node, where block node, we mean many microscopic nodes have been coarse-grained into that new node at the next hierarchical level.
Diego?
Okay, yeah.
Can I ask, this is Rodrigo, how is this different from the coarse graining you do in community detection?
Yeah, I will mention this, probably next slide.
Okay.
Yeah.
Right.
So for the moment, I mean, it's important to just focus on this absence of a metric distance, which means a priori there is no scale factor in the metric sense that can be applied. Okay. So as I said, so the typical example where renormalization plays a role and operates on lattices is when you have spin systems, for instance, on a bidimensional grid. And there, I mean, you can in principle decide how many spins you want to end up into the block spin at the next level. Like, so for instance, all the 4 spins at the vertices of a square end up being the new spin. And then you have to introduce, of course, renormalization rules that tell you what would be the value of the block spin at the next level. Okay, but in order to decide who ends up being in which block node, you use coordinates. Okay, so with network renormalization, we have this, a priori, we have this problem. So there is an explicit a priori, where there is a lack of an explicit a priori underlying metric structure. So how to define block nodes. And moreover, if we think not just about arbitrary graphs, but about realistic, real-world networks, well, we have also the problem that we know they are scale-free, typically in small work. So this brings extra complications. So really, this brings the problem to a severe condition, in a sense, because if you imagine defining, so taking from the ordinary lattice renormalization, the recipe that all the nodes that are neighbors of a given node will become the block node at the next level, you have this contradiction that you cannot make this choice symmetrical from both sides, because individual edges are seen from the two sides. And if on one side of the edge there is a hub, then the neighborhood of a hub will be a huge number of nodes ending up into the same coarse-grained node. Whereas from the perspective of the neighbors of the hub, which typically are nodes of very small degree, then from their perspective, the size of the neighborhood is much smaller. So then you would have this very heterogeneous composition of block nodes. But this construction is inherently incompatible, I mean, from both sides, if you look at the problem from both sides of the same edge. And in any case, even if you engineer some consistent recipe for doing so, there is still the small work property that basically implies that after a few renormalization steps, you have covered the entire network. So practically, you won't be defining an interesting hierarchy of coarse-grainings that you can explore. And then, I mean, very often, the very definition of nodes in a network can be heterogeneous in terms of their hierarchical level. So, for instance, you may have, say, homogeneous choices of resolution where all the nodes of your network are, for instance, banks or firms, and we are talking about an economic or financial network between these entities. But often you have heterogeneous entities like firms and countries or individuals in the same network, and then the network starts being a multi-scale one. So we would like to, I mean, define an approach that can bypass these complications. And of course, this is not the first approach, so there's been a lot of work done already in graph renormalization. And perhaps one of the earliest attempts to make this rigorous is the attempt that basically borrows some ideas from fractal analysis. And borrowing ideas from fractal analysis, like, for instance, the box covering technique that allows to compute the fractal dimension of an object, is a route that has been taken. But clearly this now assumes scale freeness. And actually this idea is based on the analogy, which can sometimes be dangerous actually, of identifying the scale-free degree distribution, so the power law functional form of the degree distribution, with typical scaling laws that you see in fractal analysis. So basically laws that tell you how much mass of a fractal is contained within a certain radius, okay? So this is a bit dangerous because actually fractals do make use, again, of an embedding metric space, right? So actually to define the fractal in the first place, you need to compare different dimensionalities. One is the topology of the object, that of the fractal itself. One is the fractal dimension of the object, which has to do with how much of the embedding space the object is covering. And then, optionally, there is also the embedding dimension of the space itself. And typically, fractals have their fractal dimension, which is intermediate between the topological dimension and the embedding fractal dimension. So, without proper definitions of this metric spaces, it's also difficult to define a fractal in the first place. And then, so here comes the idea of communities. So other approaches aim at coarse-graining a graph by making, say, the useful assumption that, okay, if the graph contains communities, then it is natural to represent these communities as the as the block nodes, so as the building blocks of the network at the next level. But again, this requires some assumption. So in the first example, the scale-free property is necessary in order to define the box covering technique leading to a fractal-like kind of analysis. In this example here, the assumption is the existence of communities. So this wouldn't work if your graph doesn't have communities in the first place. But if there are communities, then you would really like to have, again, a huge hierarchy of communities nested within each other, right? In order to have some hierarchy of partitions of the same network to explore. So there is limited iterability in this case as well, a little bit like for the small world complication. And then, I mean, this has become very popular now because it's a really powerful idea, I think. So there is this framework where you, well, there's first of all a model where actually realistic scale-free networks are constructed as random geometric graphs in an embedding hyperbolic space. So if you sprinkle points at random on a hyperbolic surface and then connect the nodes that are within a certain radius or distance with each other, then this would create, so the equivalent of a lattice, in a sense, of a random lattice, but now in hyperbolic plane. And so this random lattice will have realistic properties. So this does not start as a technique for renormalization, right? Because if you now have a real network, you first have to do the hyperbolic embedding of this network and then exploit the coordinates that nodes acquire in this embedding to now define coarse-grained nodes. So for instance, now your nodes will become a merging of all the nodes that are within a certain hyperbolic distance from each other. So here, actually, the issues or technicalities here that are required is, okay, first of all, what is a good choice for the dimension of the embedding space? So when you do the embedding, so you do not start with the hyperbolic surface in the first place, but you induce, you infer the hyperbolic structure that is compatible with the empirical network. Then you have to make a choice. So do you embed your nodes in a hyperbolic space of what dimensionality? And also, does it create a distortion? So this will not be a one-to-one mapping, of course. So if you now start back from the coordinates that you have fitted to the nodes in your network, can you replicate the original network back again? And another point here is that also this approach actually assumes power law degree distributions in the network to be embedded. So because this idea produces scale-free networks, in a sense, it is compatible with scale-free networks. So all these approaches actually are reducible to the good old case of ordinary lattices. So if you want to, say, introduce a framework for graph renormalizations where you don't want to make any assumption about the structure of the input graph, so you would like this to work for lattices, for scale-free networks, but for all other networks in between. So for all networks that are neither lattices nor scale-free. Okay. So then the question then still remains: how can we introduce a framework that works in general? And again, if you also want to have this idea of making the approach compatible with networks that have a multitude of different scales, it is not easy to engineer all these methodologies here in this multi-scale setting. Okay, so what is in the end the approach that we are proposing in this paper? Well, the idea is to basically look for a scheme that would work for any possible partition of nodes. So here we are, if you want, leaving the ground for the choice of partition to any other external method. So all the previous approaches that I've listed can still serve as approaches that indicate a sensible partition of nodes. But what we want to do with this method is to make it work for any possible partition, okay? So in this way, we avoid the problem of whether it is sensible or not to define a partition in the first place, okay? But moreover, and more importantly, this avoids now any structural assumption. So this will work for scale-free graphs or not. This will work for graphs that have been constructed starting from some hyperbolic embedding or not. And the same whether there is community structure or not, then the method will work in any case. It will work for lattices, and it will also be multi-scale. Now, if preferred partitions are useful, so if you still want to induce some special partition, so some special recipe in how you coarse-grain the nodes, then this is still possible. And it's the method itself that produces, say, the parameters for making this possible. But this is optional. So the key thing is that the method can work for any partition. So first of all, let us define the rules of the game. So we imagine a series of hierarchical levels. So the label L is denoting the particular level in the hierarchy of coarse-grainings of the network. So say level 0 is the original graph, okay? And then level 1 is your first partition, and then you may want to do a partition of a partition and so on, like in any renormalization scheme, you want to iterate it. So the graph at level L is specified by its adjacency matrix, A, and we will call it the L graph. And the nodes of that graph will be the L nodes, okay? So then the idea is to have these L nodes denoted by integers as usual. So you have node I, node J, but now this have a subscript L. So there is node I at level L, node J at level L. And then you introduce a partition that coarse-grains the network at level L to the next level, L plus 1. So now we have, in general, a smaller number of nodes, clearly, and new labels for these nodes. So there would be node I at level L plus 1, node J at level L plus 1, and this I and J have nothing to do with the previous level I and J, clearly, but there will be a mapping from the previous node, say, onto the previous level onto the next level. So this is surjective mapping, clearly, so many nodes may end up into the same node. And omega L will be the name for the partition that moves us from level L to level L plus 1. Okay, so what is the topology of the graph at level L plus 1? How is it induced by level L? Well, the recipe is that any of the block nodes, so the L plus 1 nodes, are connected if at the previous level there was at least one link between any pair of the constituent nodes for these block nodes. Okay, so if there is any link between any of the pairs of nodes across the two blocks, then these blocks acquire a link at the next level. So this is specifically conceived for binary graphs. So at each level of the hierarchy, the graphs are binary, okay? And the adjacency matrices of these two graphs, let's say level L+1 and level L, are connected via this relationship at the bottom. Okay, so clearly, in order not to observe an edge between any two nodes, you need no edge to be there between any of the possible pair of constituent nodes. So basically, 1 minus a ij at level L+1 should be the product of all the 1 minus aij's at the underlying level, where the product runs over the pairs of nodes across the two blocks, basically. Okay, so this is just how you induce the graph at the next level, given a partition omega of L defined for the nodes at level L.
Could I ask something, you?
Yeah.
About the previous, so you said it's a binary graph, so like a link in the L+1 level, you don't know how many links there are in the L level, right? It's
right.
Just if there is a link, okay.
Right.
And then so for the nodes, is there any information kept in like how many nodes there were in the previous level, or just one node?
For the node, there will be information. Yes, so you can encode that information into the parameters of the model. But in general, you may want to include a different piece of information. So I'm going to show then that this model, so to have a model that is functionally invariant across levels, you need the probability of connection between nodes to depend on node-specific parameters. And these node-specific parameters have to be additive when you coarse-grain. So basically, you will have some hidden variable attached to all the possible, to all nodes. And when a group of nodes becomes a block node, the block node acquires a hidden variable, which is the sum of the previous values of the nodes at the level. So if you want, you may start at level 0 by giving each node just the number 1 as hidden variable. So it's counting how many nodes you have at that level in that node. So it's clearly 1. But then already at the first iteration, that number becomes the number of nodes that are mapped into the block node.
Okay.
And Diego, can I just ask another question as well? So usually when you do like modularity optimization, so you also need to and you try to optimize modularity, you need to construct like also metagraphs that are made of communities, which typically weighted graphs, which is different from what you do, because in your case, at the next level, it's not weighted, it's unweighted. But in modularity optimization, you also need to add self-loops. In your case, do you add self-loops, or there is no self-loop that can be defined after one step of renormalization?
Yes, you can put self-loops. I actually recommend putting self-loops because then it makes many relationships more elegant, many mathematical formulas more elegant. So definitely yes. So for instance, in all these 3 red nodes on the right, since there was a link, at least one link between any, among the pairs of nodes that make up that block node at the next level, then you put a self-loop. Okay, so if you were to merge together a bunch of nodes that were mutually disconnected, mutually isolated, so that there was no link inside that block, then there is no self-loop at the next level. But typically the nodes are connected, there is at least one connection, and then you will have self-loops.
Okay, thanks.
This ensures that some quantity is conserved throughout the process. Yes, I mean, but I see what you mean when you say when you try to do this for weighted graphs, thinking about the expected weights of links, you can clearly make the model scale invariant in the sense that you take this bilinear choice precisely as in modularity maximization, where now your you have the expected weight of a link between block nodes is the product of the strength, basically, of the two nodes, right? So this bilinearity makes the choice Scale-invariant. The problem is that, of course, you lose all information about the topology. So that becomes an expression for the expected weight of links. And it gives you no probability of connection for pairs of nodes. It doesn't even give you the form of the probability distribution for that weight, but just the expected value. So you know how the expected value should scale, but you don't know what is the underlying probability distribution. What we are doing here is to restrict ourselves to the binary case for the moment, but then constructing the probability distribution, telling you whether a link is there or not. Okay, now the fact that the method is designed to work for any partition also automatically implies that it can work also across scales. So you see here, there are two possible ways you can regard your system. Well, the coarse-graining of your system. So imagine you specify your preferred hierarchy of partitions. So you put all the microscopic nodes as leaves of this dendrogram, and then the dendrogram will be a way that you can choose to parameterize any arbitrary sequence of nested partitions, right? So you have this sequence omega L for multiple values of L. And then you may decide that the different levels in this hierarchy are horizontal cuts, basically, in the dendrogram. And this will more or less identify homogeneous scales all the time. So again, in the example of an economic network, you may think start with firms being the nodes of your network, and then with some cut, those nodes will be merged into firms, into countries. Okay, so you will have a homogeneous hierarchy of countries. But now, if you may also want to do this multiscale, so you want to cut the dendrogram at different heights, and you would like the method to work in this case as well. Well, but clearly this multiscale partition is nothing but another possible partition of the system. And since the system will work for all possible partitions, then this is included in the possible choices of partitions you can make. So that's how, very simply, the model works in a multiscale setting, because it works for any partition. Okay, so the key step now is to introduce the probabilities for the graphs that you can generate at a given level, and to induce then probabilities at the next level. So we have to imagine now that the introduction of a random graph model, basically, where you specify what are your units of resolution at level L. So these are the nodes at level L. And then all the possible graphs that can be generated at level L will be generated with a certain probability distribution. Now, the moment you fix a partition omega, these probabilities on the left will induce another probability distribution on the right. And the only difficulty is the fact that there are multiple graphs on the left that end up being represented by the same graph on the right. So then the probability induced at level L+1 should take into account the sum of the probabilities of the underlying graphs at level L that end up being in the same graph at level L+1. Okay, but this is nothing special so far, so you can do this clearly for any random model of a graph. Simply define a partition, and then you can extend the probabilities from one level to the next. But the key thing here is that we want to impose that these probabilities at any level L, the probability of generating a graph at that level, has the same functional form. So it will have parameters, and these parameters will renormalize across levels. But apart from the renormalized parameters, the probability for generating the graphs will be functionally invariant. Okay, so they will only depend on parameters defined at each level, and these parameters renormalize across levels. So that's the key requirement, which can be stated mathematically in this way. So here you have probability of generating an adjacency matrix at level L, given a set theta L of parameters at that scale, should be the sum of all possible graphs at the lower level M that eventually are mapped onto the graph at level L of the probabilities for those graphs. Okay, where now basically the parameters at the new level, say L, are obtained from the parameters at the previous level M via some renormalization rules that we have to find. So here comes the only basically assumption of this model, so that we want to restrict the search for these probabilities in the set, well, among the set of independent models. So we want to restrict to the case where the probability of generating a graph factorizes into the product of the probabilities of individual edges. Okay, so these are very, of course, this includes a lot of models normally, like the Garlaschelli random graph, the configuration model, degree corrected block model, and so on. These are all edge independent models. And if you restrict your search within this class, then the solution is quite simple. Actually, there is a unique solution to the problem, and it's given by this probability here. So we find that the probability of connecting a node I at level L with a node J at level L depends, well, has this functional form, is 1 minus an exponential. And the parameter here are 3, basically. There are 3 classes of parameters. There is one parameter delta, which is a global parameter, does not depend on the individual nodes. This is like the parameter tuning the overall density of your network, like in the Garlaschelli random graph. Then there are node-specific parameters, x. So this x belongs to an individual node, and this is like in the hidden variable or fitness models. Actually, we will call this x a fitness of the corresponding node. And then there is a set of dyadic parameters, d. So this can incorporate distances, similarities, membership to communities. So all dyadic factors that can't be expressed in terms of node-specific ones. So all these 3 parameters have to be positive. So the function f. So f is an arbitrary positive function of these dyadic parameters. And now this works as, so this is the unique solution of the scale-invariance requirement, basically, provided that the parameters renormalize as follows. So delta is really scale-invariant, so it's a constant and does not change with the level L. X instead is additive. So when multiple nodes are merged into a block node at the next level, the x value for the next level node should be the sum of the x values for the constituent nodes. And the function f of the dyadic factors should renormalize according to this weighted average, which involves the fitness values. Now, very importantly, here f can be switched off. So if you set f identically equal to 1, for instance, then it still works because it solves it is compatible with the renormalization condition for f. And so it basically, this means that the dyadic factors are optional. They can disappear from the model, including any possible dependence on geometric coordinates. And that's crucial. So the model can live completely without geometry and be simply a model that where the connection probability depends on fitness values that are node specific. They only have to be positive. There is no metricity implied or assumed from this formula. Okay, so this is what I just said. So you cannot switch. So sorry, on the other hand, you cannot switch off the dependence on these node specific parameters. So there is no way to set these x values to a constant, because already at the next level, they will transform additively. So these numbers will change, okay? So you cannot switch off the dependence on the fitness values. So this means that the fitness model with this unique form of the connection probability, or the homogeneous random graphs, if depending on the audience, whether this is a preferred definition, can be made compatible with scale-invariance. Okay, but the dyadic factors can be switched off. Okay. Now, the functional form here is different from that for the configuration model and the degree-corrected stochastic block model. So these models, which are very popular, actually are not scale-invariant. And we know this, I mean, because people have struggled many years trying to renormalize these models. Okay. Now, the link density increases as you increase the level of the hierarchy. Clearly, by coarse-graining nodes, you will end up producing more and more links. And so even if you start from a very sparse setting where you can make this probability resemble that of, say, the Chung-Lu model, which is a kind of sparse limit for the configuration model, eventually the coarse-graining process will bring you away from that sparse regime. So, so this will really make the two models incompatible with each other, the configuration model and this model here. Okay, and importantly here, we are not assuming scale freeness, because the shape of the network will depend on how we distribute these parameters x to the different nodes, right? So this is typical in the fitness model. So you can't, you don't know how the network looks like only from the form of the connection probability. You also have to specify a distribution for this hidden variable x. So that distribution will imply some, well, the topological properties of the network. But all that I'm saying here in this slide, holds for the quenched version of the model. By quenched, I mean that you assume that the x values are fixed, are given to each node. And then when you coarse-grain, these values transform. So they are fixed at all levels of the hierarchy. We will also consider a setting where these x values are annealed. So they are resampled at each level of the hierarchy. And in that case, there is no choice possible on the distribution of the x values. This has to be compliant with the requirement of scale-invariance. And then the only possible PDF will be the Levi stable or alpha stable distributions. Okay, so let me proceed in steps. So first, the quenched approach. So as I said, now you can imagine that the fitness is given to all nodes. This is the deterministic quantity. And what makes, I think, this scenario interesting is when you have a real-world network for which there is some empirical factor attached to the nodes that, that you know has an impact on the topology of the network. So that's why we will consider an application to the international trade network, where a long series of research papers have shown that the GDP of countries in the real world have a strong effect on the probability of connection between countries in the trade network. So the GDP is a natural candidate to be identified with the fitness values that can be then plugged into the functional form of the probability. In the annealed case, instead, as I said, is a case where now you imagine that x is an annealed variable. So also across the coarse-grainings, you may imagine that the randomness in x for each node survives across all levels. So then the requirement of scale-invariance is that you want to be able to produce a network at a given level, including the fitness values with their distribution at that level, either directly, so by considering that level and reading only the renormalized parameters of the model at that level, or hierarchically again. So starting from a more fundamental level and then coarse-graining until you reach the prescribed partition. And then you want these two probability distributions to be identical. So this is the general requirement both for the quenched and the annealed case, but in addition, in the annealed case, you have to take into account the consequences for this requirement on the distribution, on the probability distribution for the fitness values. Okay, so application to the international trade network. As I said, the GDP is a good candidate here for the fitness, also because it's an additive quantity. So if you take a bunch of 5 countries, the combined GDP for these 5 countries is really the sum of the GDPs of the countries. So this will fix the fitness values. And now the distances are another important factor that has been found in the economic literature that impacts the existence of trade between countries. So you can also plug geographical distances between countries into the model. And then the renormalization rules will be this for the distance. And actually, this is a very popular, if you replace GDP with population, this is a popular choice in geography. So how to define distances between regions at different demographic levels of resolution, then this is typically how it's one of the possible ways in which you define the coarse-grained distances. What can change is the definition of this function. So here we have taken the inverse function, the inverse of the distance, because this has some economic backing. But in general, with an arbitrary function of distances, this is precisely how you would weight the renormalized distances where GDP is replaced by population in geography. Okay, so this choice leads us to this scale-invariant model of the international trade network. And now we have fixed both the node specific and the dyadic parameters. So the only parameter left is delta. There is a unique global parameter left in the connection probability. And the result that we found is that if you fit the parameter delta in such a way that the density of the network at the microscopic level is the same, the expected density is the same as the empirical density. So you take the empirical international trade network and measure the density and then set it equal to the expected density under this model. And this will be your choice that fixes delta. And then you never change delta afterwards. Then the density, assortativity, and clustering and other properties of the network are very well replicated across different levels in the hierarchy. So here there are 18 possible levels of the hierarchy where we have merged countries into meta countries or block countries, if you want, by specifying these dendrograms. And these dendrograms were based on, well, which country was nearby which country. So you see, this is a very good accordance between model expectations and the resulting network, the empirical network properties. But even at the level of individual nodes, the agreement is very good. So here you see now for each node, as a function of the GDP, the degree, the average nearest neighbor degree, and the clustering coefficient of that node. And this is for the, let's say, the natural level, the zero level of the hierarchy. So when each node is a country. And then this is a couple of examples for two levels, two intermediate levels in the hierarchy. So the agreement carries over down to the level of individual nodes. And again, there is just one global parameter being fitted here.
Diego?
Yeah.
So yes, only one global parameter, delta, but at the same time, you still have to choose all of the partitions, right? The 18 of those, that's up to you to decide, right? And you need some expert information or some other way of deciding how to choose those 18 levels of omega, right?
Yes, actually we tried with, okay, the specific choice that we made was the one that was more reasonable for us from a, say, geographic perspective. We simply took the original pairwise distances between countries, those that are already in the trade database. And then we applied the hierarchical clustering algorithm to produce a dendrogram where basically then at the upper levels of the hierarchy, you have groups of countries that are closer to each other than with other groups. So this is a way of creating a regional aggregation based not on political borders or continents or history or whatever, but based on the actual geographic distances. This is what made our choice, I think, sensible at least, but we tried, since we insisted on this invariance on the partitions, we tried with really crazy partitions as well. So putting together countries that do not belong to the same continent and all kind of weird aggregations, and it still worked. Only we were
so it works in that the observation and your prediction more or less match, even though the partition might not be sensible. Like you're putting Japan with the antipode. Okay.
Yeah, because here basically what you need to check is whether at a given hierarchical level the method works in the connection probability works in the first place.
Yes.
Right. Okay. So if already at level 0 the real network is not replicated by this connection probability, then I mean there's no point in moving farther. Okay. But once you have identified a good match between the model and this probability, and this probability in a sense comes from first principles, so it's not coming from an a posteriori fit like in the gravity model literature, for instance, that you see that most of the trade volumes are replicated by this product of GDPs divided by distances. But it's rather comes a priori from this functional form that has to be Scale-Invariance in our approach. Then if there is a match, then there is hope. You can carry on with this probability function using any partition. Still, we wanted to make kind of sensible geography-wise sequence of partitions, so we use this dendrogram of nested geographic partitions. Okay, last thing, and I think I have just 1 or 2 minutes left. The annealed case. So as I said, the annealed case is now where the case where also the x values are seen as random variables, not only the graphs themselves. And now the requirement of Scale-Invariance immediately leads to the class of Levi-stable distributions. So still we have the probability function that we use in the Quenched case. That's the unique form of the probability of the connection probability. Now that will be combined with this Levi-stable distribution of the fitnesses. Okay, so if you want, okay, we have required that the fitness values have to be positive. So this restricts the range of exponents for the Levi-stable class. If you also, then you also want the support of this PDF to be Scale-Invariant. So you don't want the support to move to infinity as you proceed with the coarse-graining. So this basically selects a range of parameters, in particular the parameter alpha of the Levi-stable should be between 0 and 1, within which there is just one analytically known form of the probability density function, which is the Levi distribution, where alpha is 1/2. So this is the only known enclosed form in the range consistent with Scale-Invariance in the sense we are defining it here. And okay, so this will be how the fitness distribution looks like. Very important, this distribution itself would be very bad for the degree distribution, because this is not in the range of exponents observed for the degree distribution, which has exponent between 2 and 3. This is exponent 1/2, but it's for, 1 plus alpha, so it's probability 1.5, but this is for the fitness. Now, if you combine this with the PDF, with the connection probability, you find what the degree distribution is. And basically this form here that can be found exactly has a power law decay with exponent -2, followed by a cutoff at large values of the degree. Well, this cutoff actually means that when you aggregate very much, then you reach an almost fully connected network. So all the degrees will have value n-1. So this is the kind of cutoff that you obtain from this. So you get an exponent, a good exponent now. So degree decaying as -2 because of the combination, because of the fact that you have to do this convolution of the fitness distribution with the connection probability. And then finally, last slide, also the assortativity and clustering properties. So the average nearest neighbor degree as a function of the degree and the clustering coefficient as a function of the degree look quite realistic in the sense that they have this typical decaying shape. Okay, so thanks for your attention, and well, thank you again also for the invitation to give this talk. Thank you.
Yes, thank you very much. So are there any other questions for Diego? Or if someone prefers to type in the chat, that's also possible. Just,
if I may, I'm gonna ask away one. Oh, there's one in the chat. Good night. So if I may again, Diego, yeah. I was interested when you were saying that so in the sparse limit this is compatible with the, for example, the degree corrected SVM, but obviously as you move into the higher hierarchies, that's no longer sparse and it breaks down, right? And your model renormalizes as well. So what breaks down in this, for example, in the degree corrected SVM? Is it because in principle it's more or less similar, not the whole process of calculating the probabilities, but how you aggregate, how you do a nested SVM. For example, it would be similar apart from the fact that you're keeping track of the edges and you're summing, like Renaud was saying, no? So
what breaks scale-invariance in the configuration model and the degree corrected stochastic block model, which is nothing but adding dyadic factors to the configuration model, right? Mm-hmm. Is the fact that the degrees do not renormalize additively through the process. So right. Even if at level 0, that model replicates your real graph very well, when you move to the next level, you can't compute the degrees as the new degrees simply as sums of the degrees of the pre-existing nodes at the previous level.
Okay, yeah.
Whereas in this model here, the degrees will be produced and they will have some value. But what keeps the scale invariance is the fact that the fitness values will add up. So they will transform additively. Also, the fact that the model here reduces to the, say, Chung-Lu or configuration model in the sparse case, it's not completely true. Well, it has to be contextualized at least, because in the annealed case, this is not the case. So in the annealed case, the functional form of the probability here, okay, you may think, if you look at the probability as a function of delta, I take a delta so small that this becomes roughly delta times xi xj times f. This is a Chung-Lu model in the end, if you switch off the distance, right? And if you put the distance as blocks, this is the degree corrected stochastic block model, where x in both cases would be proportional to the degree of node I. Now, actually, there is a subtle assumption here. So here, to have this p approximated by that expression, you need actually xi xj times f be very small, so much smaller than the inverse of delta for all pairs of I and j simultaneously. But now, if the distribution of the x values is extreme, as in the annealed case, because then it's a Levy distribution, actually, there is no such regime possible. So in this case here, indeed, you see that also in the very sparse case, which is the blue curve is a sparse case here, you see that the fitness decays as x to the minus 1.5, but the degree still decays as -2. So they can't be proportional to each other. So the degrees and the fitness are not proportional to each other, not even in the sparse regime in this case, because the variance in the fitness is so big that for no value of delta, you can approximate that probability as the product of xi, xj, unless you really take your network to be completely fragmented. So that regime only exists below the connectivity threshold and the percolation threshold for this model.
Thank you. Are there any other questions? If not, let's thank Diego once again. Thank you very much for joining us, Diego.
Thank you. Thanks a lot for the invitation again. And of course, I'm available via email for comments or questions.
And we also linked your the preprint in our advertisement. So if you want to read it, just read our emails. It's there.
Okay,
and
thank you.
On the screen right now. Thank you, Diego.
Thanks.
Okay, so see everyone next week. Bye-bye.